Welcome to CS3308 Information Retrieval. This is the Unit 2 lecture part 2. In this lecture, we're going to talk a little bit about the data structures that we might want to use to implement the dictionary. Now, we've talked a little bit about the fact that as part of an information retrieval system, I'm going to build a dictionary, and the dictionary is where all of the terms are going to go. And in some cases, I might actually want to build two different dictionaries. I might have a dictionary where I put all of the terms and I assign a number to that term, right? So that way I'm not having to keep that term. Maybe it's a string of 8 or 20 or whatever bytes. I might want to just say, hey, I know there's a term and it's the word catastrophic and it has a integer number of 32,582, right? And the reason I want to do that is because I can keep that integer number of 32,582 in a much smaller amount of space than I can keep the actual term catastrophic. So dictionaries I would use in that way, and I can use that both for terms, so those are all the things that I'm searching on, as well as perhaps the name of document. So for example, a lot of times in the postings list, what I'm going to do is I'm not going to have the name of the file or the document, but in fact I'll have a number where I've associated a number with that particular document, and I'm keeping that data in a dictionary. So what we want to look at here is just the data structures that we would use for a terms dictionary. Potentially we could use a similar concept with the postings dictionary as well, but basically the data structures that I'm going to typically use for inverted indexes are going to have a couple of different elements. So for example, we have talked about the fact that I'm going to have the dictionary, and basically the dictionary is just where all the terms are, right? The words that I might be searching on. And then I'm also going to have this concept of a postings file. And essentially the postings file says what, this term appears in this document. Now you notice that I'm representing the document as a number. And so essentially the assumption is that somewhere out here I'm going to have a document dictionary where it's going to say the number 1 refers to a document with some name. So maybe it's file1.txt. But both of these things exist. Now, the challenge that I have with this particular structure, the dictionary, is that it's going to get relatively long. I mean, it's going to have all of the different words that I might potentially search on. So I have to have a way of finding them rather quickly. The one thing I don't want to do is I don't want to have some file that has all of my terms in it and have to sequentially search through it, because we know that's going to take a long time. The reality is I could literally have hundreds of thousands to millions of different terms. So the challenge that I need to do is I need to think out, well, what data structure would I want to have to put these values in that is efficient and allows me to find them quickly. So there's, a challenge here, right? Because one of the things that we run into is size. And the reality is that I can have very large numbers of terms, particularly if I'm using, for example, one of the reasons I might want to get rid of the stop words, and we've talked about the stop words, is because there's a lot of them potentially. So I really don't want to have those terms that are out there. So essentially, I have this kind of a structure, and generally I want to try to put that entire dictionary in memory. Now, why do I want to put it in memory? Well, the reality is that when I put it up in memory, I'm going to have much faster access to it. So reading data out of memory is going to be much faster than reading data from a disk. So I want it to be efficient in terms of the ability to search through it quickly, and I also want to make it efficient such that I could keep it in memory, because regardless of what structure I use, the ability to keep in memory means I'm going to have a little bit faster access to it. So what are the different options that I have for structures to put that dictionary in? And there's basically two main choices. One of them we kind of refer to as a hash table, and the other one is a tree. Now, let me just address the idea of a hash table and what it is. So basically a hash table is a data structure where I take every single term and I hash it to an integer. What do you mean by hash? Well, I apply some kind of a mathematical process to it that converts the term. Maybe it's a word that uses letters, maybe it's a combination of letters and numbers, whatever it happens to be. But I apply some process to it mathematical process to it that turns it into a integer. And one way of doing that, for example, is to, let's say it's a word, and I'm going to take the ASCII value of every character in there and I'm going to add them up. That would be a way of hashing it. Now, obviously, there's an advantage to this because it means that I can convert a word into a hash very quickly, and I can look it up very quickly, right? I don't have to search anything because all I do is I convert it into the hash, and then the hash becomes the key to some form of a table that I access it to. The problem with hash tables is that a lot of times they're not going to be unique. So it's difficult to come up with a hash strategy that's always going to evaluate into a unique number for that term. So that's one of the problems. There's some other issues with it as well. One of them is the only thing I can really search on is the exact match of the term. So there's kind of no prefix searches, there's no wildcard searches, etc. So it's really difficult to deal with things where I might only want to search a portion of the word, as well as things where I might want to find minor variants of the word through the use of wildcards, right? And then the other thing that we run into is that as the vocabulary gets larger, I might have to do more and more sophisticated hashes to ensure that the vocabulary or the dictionary is consistent. So it becomes rather expensive to have to rehash stuff over and over again. So hash tables sometimes work, sometimes no. The alternative is to use some sort of a binary tree structure. Now, the way that a binary tree structure works is that essentially I take all my data and I kind of put it in a sorted order. And when it's in a sorted order, I can kind of lay it out into a tabular format. And what does that mean? Well, imagine, if you would, that I take all my data and I say, okay, anything that's going to start with a letter from A to M, I'm going to put on the left hand side of this file, and everything that's N to Z is going to be on the right hand. And then within A to M, I might have the ability to say everything that is A to HU. Basically, the idea here is, you think about it, if I had A, B, C's, D's, E's, and F's, and we're going to stay right there, right? So the easiest way to find, let's say that I'm looking for the word boy, right? The easiest way to do that is I can come in and I can say, hey, I'm going to go halfway through the list. I'm just going to randomly split it in half, and I'm going to say, where am I at, right? Is boy below where I'm at or above where I'm at? Well, we know it's below where I'm at, so I can say, okay, I'm going to take this part here, and I'm going to split it in half again, okay? And then I'm going to say, is boy below where I'm at or above where I'm at? And I can say, well, it's actually below, and then I'm going to split it in half again. And you can see how I very quickly narrow down where boy is at. This is the whole concept of a binary tree structure. And we're going to also look at the B tree, which is kind of a little bit of a modification of it. Now, binary tree basically means one thing. Binary means 2, 0, 1, and base 2. And that basically means that every node only has 2 outputs from it. So essentially, because it's binary, the tree tends to grow a little bit higher, right? Because of the fact that I only have 2 options. So every time I come to an option, I have to split off into another depth down. Now, this depth of the table determines how long it takes me to search it. So, for example, if I had to search for boy in this list, it would be pretty good because it's near the top. However, if I had to search for something with F in it, I might potentially have to go all the way through the list. And if my list is long, such as in hundreds of millions or billions of terms, like I might have with Google, it can take a long time. So B trees tend to be dramatically more efficient in terms of the ability to search for a particular piece of information. Many information retrieval systems are going to use some form of a B tree or binary tree search, simply because they are so efficient and they don't have the disadvantages of hash tables. A slightly different form of this is the B tree. Now notice we're not binary. We're going to call it B tree. And what's different about this from the binary tree is, as I said before, binary means two, which means any particular level can only have two outcomes. In a B tree, I might have more. And the whole idea is that it just depends upon how many items that are out there and how well you can split them up. But in the B tree, I might actually leverage multiple options coming out of it. So in this particular case, the level has 3. In this case, the level has 4. In this case, the level only has 2. But again, it's going to be highly dependent how many children you have based upon the data and how the data breaks out. So again, trees are going to be one of the most efficient things that I can do in terms of storing my dictionary. The simplest ones to implement are binary trees, but again, the problem with a binary tree is, although it's very simple to put together and implement, and the data structures necessary to put it together are very simple. All I got to do is order stuff in alphabetical order. It has a disadvantage in the sense that the height of the tree starts to grow when I have lots and lots of items. So it can actually be a little bit time consuming when you compare it to the B tree that doesn't have that restriction of just 2 nodes or 2 children coming out of it. So again, one of the advantages of the B tree over the hashing is that it solves that prefix problem, right? Because I can actually start searching those terms within the B tree using wildcards. So, again, the example we looked at where we just had A, B, C, D, E, and F, presumably within A, there's a whole series of words, right? But I could kind of start at A star, and then I've narrowed perhaps my search down, and then I just scan through the remaining units. So every way you look at it, B trees and or binary trees provide us an advantage from a prefix problem, as well as the ability to do wildcard searches. Now, some of the cons to it is that it can be slower. I mean, obviously, a hash table is very, very fast. It's big O1, right? Whereas in a B tree or a tree structure, it tends to be big O of log of M. And basically, keep in mind that when we start talking log, it means it's a structure that kind of looks like this, right? And so it rapidly grows, but then it tends to taper off. So even though it is slower, it is very efficient because, you kind of quickly reach a point where it doesn't grow anymore in terms of the amount of time it takes. So one of the other big challenges with B trees or trees in general is the need to rebalance them. So if I go add a whole bunch of new terms, I suddenly have to resort it or restructure it or put it, change it in some way such that I've got all of the entries in the appropriate order. So that's one of the disadvantages. Hopefully this gives you a good sense of the kind of structures that we're going to use for dictionary items. In our example or in our assignments in the class, we're actually going to use SQLite. So we're not going to go through the work of actually implementing this and the code of implementing this using Hadoop. We're just going to kind of take advantage of the fact that SQLite, being a database, will automatically put stuff into a B tree format. So we're going to get that efficiency out of it.